In this review, we are going to review the idea of sequences. So let's talk about some basic things that we learn in the class. So what's a sequence? Sequence is a list of numbers. Sequence is a list. It can be finite or infinite. Finite or infinite. So we have finite sequence and infinite sequence. For example, if you are in computer science, the finite sequence are very important. And if you are in mathematics, we normally focus on infinite sequences. Okay, so sequence is a list of finite or infinite of numbers. Okay, numbers. So it's just a list of numbers is called a sequence. So how we write it? We write it as a1, that's the first number, and then a2, comma a3. So we are simply separate them by commas. So this is an infinite sequence. So I put 3 dots to mean that it's going to continue forever, because it's an infinite sequence. So there are several ways to represent. So there are uh, several ways to represent. Okay, there are several represent. So what is the basic, very common way is we just use the set notation, like a curly bracket, and then we just list the numbers. So 1/2, let's say 1/4, 1/8, like that. So that's the most common way. We just list the numbers. The second one is we can write a formula for that. So for example, we can say this one as, so it is, so you can see this is the powers of 2, so we can write as like powers of 1/2 actually. So it is 1/2 to the n. So you can see, so this is another way to write it. So we can be more specific about this one. We can say 1/2 to the n, and we can say what is the starting value. In this case, the n has to start with 1, so we can say n going from 1 to infinity. And also there's another way, we just write the nth term. So like let's say nth term, we normally say an, which is simply 1/2n. So so we can write in several ways. So these are like 4 different ways to represent a sequence. Now let's do a problem. So let's say like a problem like this. Find a formula for the general term of the sequence. So let's say find a formula for the general term. Find a formula for the general term of the sequence. Okay, of the sequence. Let's say your sequence is given like this: 3/5, that's the first term, and then let's say second term is negative 4/25. Next term is positive 5/125. Next one is negative 6/625, like that. So we put 3 dots to mean that's going to continue. So there are few things that you can notice. One thing that you can notice from the bottom is you can see these are simply powers of 5. So the first one is 5 1, second one is 5 squared, third one is 5 cubed, fourth one is 5 4, like that. So that's how you get the denominator term. But numerator, you can see that it is simply consecutive numbers. So 3 4 5 6. So you notice that it's just the consecutive numbers. Now the thing is that you're going to pick an index. So for example, so it's just up to you how you're going to index it. So you can index it 0, you can index it 1. Let's say you're going to index it 1. Okay, so if you index it 1, what's going to happen is you can see that so the nth term can be so simply 5. So if the first one has a 1 and the second has a 2, so that means it is 5n. So we're gonna go with so your index is, let's compare with the, so let's say first one has index 1, second has index 2, third has index 3, like that, and then you can see that is exactly match the index. So if you say first one which has a 1, so that means, so that's why I would n here, and then you can see that, so in the top it is not 1, It is 1 plus 2. Second one is 2 plus 2. Third one is 3 plus 2. So that means it is n plus 2. That is what is in the numerator. And also, so that's the numerator and the denominator. Now you can see that there's also sign change. Sign change means it is -1 to some power. And then you're going to figure out what is the power. If you put n here, and then when you just n here, then you can see that when n equal 1, it is -1 to 1, which is negative. So that means it cannot be n, it has to be either n minus 1 or n plus 1. So it doesn't really matter. So we're going to say n minus 1. So, so that is the nth term. So this is the nth term of the sequence. Okay, so so we can do things like that. Good. Now let's talk about the most important one, what we call the convergence and divergence. So what is the convergence and divergence? So converging, and diverging, converging and diverging sequences. Remember, sequence is just a list of numbers. Okay, so there's nothing much. So there's a big difference between the sequence and series. When you come to sequences, there is only one test. But when you talk about series, there are a lot of tests. So, so when you come to sequences, there's only one test. So that's the interesting part. We just check the limit. If the limit exists finitely, sequence converge. That's it. Okay. So the test for convergence, there's only one test. Test for convergence. Test for convergence. So there's a simple test. So what it says that if the limit n goes to infinity, an, so n means n term, equal L, let's say this is a finite number, just a number, not infinities, then the sequence an converges. You can say especially converges to L, and that's it. Okay, that's only one result. So what do? You just check the limit. So if the limit exists, sequence converge, just one result. So otherwise, so we can say otherwise means limit not equal to constant. Not equal to constant means it can either fluctuate or goes to either positive infinity or negative infinity. So there are three things. It can go to positive infinity, or it can go to negative infinity, or does not exist, like fluctuate between several values. Okay, so otherwise it diverges. Otherwise it diverges. So very simple. Okay, diverges. So that means so that is if the limit n goes to infinity, an equal either plus or minus infinity or does not exist. So there are three cases: plus or minus infinity or does not exist. The sequence diverge. Sequence diverges. And that's the same thing. So this result is again applies to series, and we know that if you look at the nth term, if the limit but in that case what we normally say is if the limit are not equal to 0, so there's some kind of relation between the two. Okay, if the limit not equal to 0, then the series diverge. But here what it says that if the limit is plus or minus infinity or does not exist, then the sequence diverges. Okay, so see the difference between the two. So let's look at what is the graphical representation of this one. So what we can see graphically is like these kind of situations. So so one basic situation is, let's say the sequence means you can evaluate at discrete points. So these are continuous discrete points. So that's the n. So you can see you get the exact same value. Okay, so that means you see that all the values stay the same. So that means the sequence converges. So this is one very nice example where the sequence converges. You get the exact same value every time. Okay, whatever the value, exact same value. Can be positive, negative, 0, anything. And another one is something that you can actually easily see. Let's say you start with a larger value at 1 and then at 2, so it's going to go down like that, and then all go closer and closer to 0. Okay, go closer and closer to 0. So this is one nice situation. They are in this case also sequence converges. So all nicely goes to 0. So you can see if you draw a line, so you can see this line kind of going like that. But there's no line because this is continuous, but these are discrete, but it still follow a line. So you can still make an argument using a continuous function. Same here. So you can see that's the line you're talking about. Even so, those all the dots sitting on that line. Okay, and the other case is like something like this. Um, so this is like most common situation. So what happened is, so let's say there's a value, so that's the L value. So what happened is, you don't see these nice patterns here, but you can see like a one dot like here, and the other dot over there, and then next one is over there. So it's gonna jump, but still you can see every time it's getting closer and closer to this value. See, so closer and closer. So that means if you draw the curve, if you just draw a curve passing through this line, so this is what you notice. You notice that it's gonna go like that, go like this. So you see it's like getting closer and closer to this line. So that's the other case. So this is the most common case. Like those numbers like kind of fluctuate, and so those are all the cases where you can say the sequence converge. So this is a graphical situation is sometimes easy, but remember these are discrete values, but we can still use a continuous function to make an argument even though they are discrete. Okay, so that's the graphical notation, graphical way to see it. But let's look at some special cases. So how about these? So some examples. So I'm going to few sequences. Let's say as the first one, let's think about the sequence 1, 1, 1, like all 1. So you can see that the numbers are 1. So that means, so what happened? So if you look at the, so you can see the series converge because they stay in just one value, So that means the sequence converges since if you look at the nth term, the limit of the nth term is simply 1, just 1, every time 1. So this is a finite value. Okay, sometimes to mean find that we sometimes say like that means that less than infinity means a finite value. That's like a mathematical way to say it. So it's converge. Okay, because just 1, limit is 1. So what we check whether limit exists as a finite number. That's it. If you check whether the limit exists as a finite number, sequence converge. Okay, that's it. That's the only test we need for sequences. Check whether the limit exists as a finite number. So how about this one? So we can say 1, negative 1, 1, negative, no, let's put the negative 1. So it's just 1 and negative 1. So what happened? So if you see that, if you look at the graph, you can see it's gonna jump between the two values. It never go and never getting closer to one particular value. So that means the series diverge. The sequence diverges. Since what's the reason? The limit does not exist. Limit when n goes to infinity, an does not exist. So the sequence diverge. Okay. So here the sequence converge because limit is 1. Here sequence diverge because the limit does not exist. Very good. So how about this one? So maybe a little difficult one. Let's say 1, 0, and then 1, 0, 0, 1. And then you have 3 zeros, 0, 0, 0, 1, like that. What do you think about this one? So you can see that there are a lot of zeros and the number of zeros increases, but still there is a jump at one point. Okay, because there's only 1 zero here. There are 2 zeros there. There are 3 zeros there, but still after 4 zeros you get a 1. After 5 zeros you get a 1. So what do you think about this one? And you can see that this sequence still diverges because it's going to jump at one moment. Okay, so this diverges again since the limit n goes to infinity, an what does not exist because it's not one value, it's always jump to one place, stay at 0 but jump. That means there's no particular value. Okay, yeah, good. Now let's look at a like a little more algebraic problem. So how about this one? 1, -1/2, and then 1/4, -1/8, like that. So the best way you can see that these are powers of 2, powers of 1/2 actually, powers of 1/2, 1 over like a 1 or 2 to the n basically. And they are also sign chain. So if you write the n term, so the n term an, which is the negative to the sum power, so I'm going to leave it like that. And then you can see it's a 1 over 2 to the n, and then you have to figure out what is the n. So because we normally start with n equal 1, so that's like a tradition. We normally start with n equal 1, so you have to be careful with that. So that means in this case, if we go like that, to get 1, this has to be, when you plug in, so I mean it's 2 to the 0, that means this has to be n minus 1. Then you're going to get, when you apply n equal 1, it's 2 to the 0, which is 1, so you get the first term, and you have to also get the sign. That means it can be n. If you put n, then you get -1 to 1, that is negative, so that means n minus 1. So that is the n term if you use the index n equal 1. But if you use the index 0, you can simply write this one as an -1. If you use 0, it is n over 2n. So you can see that it's depending on what's the index you use, but here we can use the index 0. But that's not very common. We normally go with the index of 1. So okay, now again let's check the limit. So we can check the limit. N goes to infinity, an, so it's the limit. N goes to infinity, -1 to the n minus 1, 1 over 2 to the n minus 1. Okay, how to make the argument here? You can see that this number is kind of bounded. It can be the 1 or -1, and that's it. It's never going to grow more than that. So you can stay with between 1 and -1. But the denominator here, you can see that it grows indefinitely. That means you are trying to divide by a very, very large number. So that means this simply, because since the denominator goes to infinity, you can see this whole thing is going to fluctuate between positive and negative values, but every time it's getting smaller and smaller and smaller by with the magnitude. Magnitude is getting smaller. So that means at the end, this limit is simply 0. Okay, it's going to fluctuate, but it goes to 0. So that means if you draw a graph, because this is useful, so you can see that it's going to fluctuate. It's going to start like so. It's going to jump, and then but every time it is getting smaller and smaller. So like that. That's what happened. Okay, but you can see it's getting smaller and smaller, so it goes to 0. So it means it's limit 0. That is a finite number. It's a nice finite number. That means the sequence converge. So you can see an goes to 0 as n goes to infinity. That means the sequence an converges, because it's just a number. Okay, so you get a nice number. So that's it. So the sequence converges to what? Converges to 0. If you need to say converges to 0, you can say that, but sometimes it just whether converge or not. So it's converges to 0. Good. Okay, so let's look at more examples. So how about this one? So let's do a little bit more complicated problem like this. So D, not D, I think it's E. Yeah, but don't worry about that. So let's say an, which is 2 to the n squared minus 1 over 3n squared plus n plus 7. So limit n goes to infinity, an, so it's a limit n goes to infinity 2n squared minus 1 over 3n squared plus n plus 7. So this is a very interesting problem. When you have polynomials or algebraic expressions, just consider the dominating term, the largest term. with the coefficient. So that means you're going to pick this from the numerator and this from the denominator, because that's the largest term, the dominating term. That's the only one that matters when n goes to infinity, because these are really large numbers. So other numbers does not really matter here. So that means it's a limit n goes to infinity. So you can see 2n squared over 3n squared, and then you can see this get cancelled. So you simply end up getting 2/3. So what happens is, if the leading terms have the same degree, you just get the two coefficients. Okay, so you get, and then sometimes some people try to use the L'Hopital's rule. That is just a waste of time. You don't need that when you have problems like that. Just go with just look at the leading, the dominating term. Okay, consider only the dominating term. So consider the dominating term. Dominating terms. Remember, with the coefficient doesn't matter. That's why we put 2. So that's it. I mean, that's the only thing we have to do. Consider the dominating terms. That's always work when you have algebraic expression. So rational functions are part of the algebraic expressions. So we have any algebraic expressions, you can do that. Just consider the dominating term, and you can see this is just a finite number. So this is a finite number. It's not infinity. So that means the sequence converge. So in the sequence converges because the limit exists, and that's it. So you don't want to use the L'Hopital's rule for this. We can do problem with L'Hopital's rule, but not this one. Good. So if you want to say converge, it converges to 2/3. Okay, converges to 2/3. So if you want to write it, so you can say it converges to, in addition to 2/3. Good. So let's do another problem. How about this one? So this, I'm going to put like a really complicated one. I'm always going to use n, it doesn't really matter. So it's n cube plus 1 square root. Why I do this problem? Just to show you how powerful this is. 2n, let's say n plus 1, or even like n minus 1. But be careful with what you get here. So yeah, let's say minus 1 square root, and then plus n, and then let's say minus 3. Good. So you have to be careful with what is the index, because you don't want to divide by 0, but just forget about that part right now. So what you're going to do is you only need to, so again the question is whether the sequence converge or diverge. It's the same problem. Now what we can do, again we're going to look at the limit. So it's a limit n goes to infinity a n. So what you want to do is you only consider the dominating terms. So limit n goes to infinity. So the dominating terms are here. That's the dominating term with the square root. And then here you can see we have n here. We have n and another n is square root. So that means that is the largest term here. So that means we're going to forget everything else. So that means we can write only the dominating terms here. So it is n cube square root coming from the numerator. From the denominator, 2 comes because that's a product, n and square root n. So that's what comes from the denominator. So that's exactly the same. If you look at the limit, you can see that it's exactly the same. Now we can simplify this a little bit. Okay, and then so you can see we don't need the L'Hopital's rule. If you use the L'Hopital's rule, it's going to be very complicated. We don't need that. And then you can see in the top what we have is n 1.5 or like 3/5. In the bottom you can see 2n again 1.5, because 1/2 means square means 1/2, and you can see these two get cancelled. So you simply get 1/2, and you can see how quick. If you use the L'Hopital's rule, it can be very complicated. Maybe you are still taking derivatives. You don't need that. Okay, so and this is a finite. So that means the sequence converge. Okay, very complicated looking problem, but it's very simple. So you can see a n goes to 1/2 as n goes to infinity. So thus converges. Okay, sequence converges. I will say it's time, so I'm just writing like short form. Okay, now let's try to go to the what we call the L'Hopital's rule, because that's one of the powerful results. There are some problems that be very useful, so let's look at that problem. So the L'Hopital's rule. L'Hopital's rule. Some people don't like to say it's L'Hopital's rule because it's not really him who found this, someone else found it. So, but still we kind of call it. Okay, so L'Hopital's rule. So how to use the L'Hopital's rule? Why we can use the L'Hopital's rule? Because we know that the L'Hopital's rule can be applied in three situations. One is we have 0 over 0. That doesn't apply for these problems. When we have infinity over infinity, we can also apply L'Hopital's rule. And also we can apply the L'Hopital's rule when you have infinity times 0. So those are the three cases where we can use the L'Hopital's rule. So what we have in sequences, mostly this and that. So those are the two cases we're gonna encounter, but we can still create a problem where you get 0 or 0. The reason is n goes to infinity. So that's why we're gonna get one of those cases. So what the result is a limit n goes to infinity. So you have a function of n which should goes to infinity, and then gx which is also should goes to one of the infinities. Then it says that this is exactly equals to the limit n goes to infinity of the derivative. So we can take the derivatives of this function divided by derivatives of the bottom function. Okay, so there are a few assumptions that we make. So you can see that n is a discrete variable. But here we just kind of use a abuse of notation and we assume that n is a continuous variable. Okay, so what exactly happening is, it's clear. I'm gonna explain just once for anybody who's kind of curious what's really going on here. So that's the actual curve, but what we are doing is we are picking these values. But you can see there's 1, there's 2, and there's 3. So you can see, so we are just picking those values, but you can see that those values still follow that continuous curve. So that means instead of like a n variable, you can consider x variable. X is a continuous variable. So just by abuse of notation, we are not really going to change it. We just still use n, but make sure we are using the continuous variable, not the discrete variable. Okay, so but we just write n. Okay, but still what's going on is we are actually not really using n, we are using x. Okay, that's something you have to keep in mind. Okay, and then we're just going to continue. Okay, so if you get again two functions which both goes to infinity, then you can take the derivative again. But if stops, one of them stops, it's not going to infinity, then you cannot take the derivative anymore. You have to stop right there. But if it goes to infinity, you can keep taking derivatives. Okay, that's the interesting part. Okay, so we can do one problem like that. Okay, so good. So now, so this is the L'Hopital's rule. Okay, so let's try to do a problem or two from this one, because this is like one of the powerful results. So this is the reason. So we can use the number 2 here, infinity over infinity situation. It can be one of those infinities, not really positive infinity. So this has to go to one of plus or minus infinity. This also has to go to one of those infinity. It doesn't matter which one, but it has to be only one. So you cannot switch between the two. Okay, so you can stay with one, stay with positive infinity, bottom one stay with negative infinity. That's perfectly fine. But if they switch between the two, you cannot use that. Okay, so it has to stay with one, only one. Okay, so let's look at as the first problem like this one. So example, so let's check the convergence of this sequence, which is the n term is ln n over n. So that's the sequence. So maybe let's say your starting value is 1 to infinity. Okay, sometimes even ignore that. Okay, so in this case you can see that a n is the ln n over n. For example, if you plug in n, you get 0. The first term is 0. So the question is whether this sequence converge. So this is not really obvious because ln also grows, n also grows, but little slower than the n function. So what we do is, as before, just take the limit. So okay, so let's take the limit a n, and then limit n goes to infinity ln n over n, and then you can see that now we use the L'Hopital's rule. So we use the L'Hopital's rule here. LH. So why we can use the L'Hopital's rule? Because the top and bottom goes to infinity. So let's take the L'Hopital's rule. So if you use the L'Hopital's rule, considering n as a continuous variable, ln n, that means it is 1 over n. Our bottom n means is 1. And you can see when n goes to infinity, top goes to 0, 0 over 1, that is 0. Perfectly fine, which is a finite number. Okay, this is a finite number, no fluctuation. So looks great. So that means sequence converge. Okay, so the sequence converge. So an converges to 0. Okay, but simply it's converge. Okay, so you can see this is how we use the L'Hopital's rule for a problem like that. Okay, so let's look at another problem. So how about this one? So the next one. So we can say just something. Okay, so let's say you have like a 3n plus 2 sine n in the bottom, and you can see 4en minus n squared, something like that. Okay, so that's a sequence. So you have sequence like that. So this is the n term. Again, what do you do? Take the limit. So limit n goes to infinity an. So it's a limit. So I'm writing everything. So that's why it's gonna take time, because just to write these. But yeah, I can skip these because otherwise the argument is wrong. So as a mathematician, I cannot do that. Okay, good. Now you can see the top goes to infinity, and the bottom also goes to infinity because en grows really large. So we can use the L'Hopital's rule. So if you use the L'Hopital's rule, you can see limit n goes to infinity 3. If you take this is 3 minus 2 cosine n over, so what do you get? 4en minus 2n. Okay, now can we use the L'Hopital's rule again? And you can see that you cannot use the L'Hopital's rule again. The reason is the top does not grow further. It's not going to infinity. You can stuck at you can see, because the cosine n because there's a negative sign, because the cosine n is in between -1 and +1. Okay, so that means the largest value the top can take is 5. Why 5? Because when the cosine n is -1, because these negative signs become +2 plus 3 5. So the largest value of the numerator is 5. Okay, but since we have the exponential function in the denominator, it grows indefinitely. So that means the top is stuck at 5, is bounded by 5, but the bottom grows to infinity. Okay? Bottom function goes to infinity. Well, you can ignore this one because we have an exponential function, that's the dominating term. So we don't want to worry about 2n anymore. So en goes to infinity, but the top is stuck at 5. Okay, the top is stuck at 5. So that means this whole thing is 5 divided 5 over a large number. So that means it is simply 0. Okay, so 5 over infinity. So it goes to 0. That means the sequence converge. Okay. So an converges. Good. So we use a L'Hopital's rule and a basic argument. And even in this problem, you can see that en grows much faster than n. So you can see that this goes to 0, like just looking at the dominating term, because here the dominating term is this one, here the dominating is that one, and you can see this en grow much faster because 3n is just linear, it's just a line. Okay, that's just a line, but the other one grow like exponentially. So you can also like make an argument like that. That's also a valid argument. Okay, so this sequence converge. So the note is, so we can have like a simple note like that. So some people like to make this kind of arguments. So you can see denominator grows with a higher rate. Okay, the rate is the important one. Higher rate, with a higher rate than the numerator. Okay, so denominator goes with a higher rate than the numerator. So at the limit, the ratio between the two, that means an has to be 0. Okay, that's like another argument that you can make. Okay, so let's look at another problem. How about this one? Let's say your n term is simply sine n over n. So if you have sine n over n, but what we know, since sine n is always in between 1 and -1, so the numerator is stuck between 1 and -1. Okay, the largest value is 1, but the numerator grows indefinitely. So that means the limit has to be what? Limit of this function when n goes to infinity, sine n over n, because sine n stuck with large value is 1, and then but n grows indefinitely. So that means this has to, is like a 1 over infinity situation. So it's 0. Good. So that means the sequence an converges. Converges. Okay. So let's look at what if um, you have something like n times, let's switch like n upside down. Like how about this one? So let's say it's like a simple variation of this problem. So let's say an is given by n sine 1 over n. This is an interesting problem because we can do this problem also in the series, with series. What's going to happen with series? So let's look at this problem. So one thing you notice is, you can see this is n goes to infinity sine 1 over n. When n goes to infinity, 1 over n goes to 0, but sine 0 is 0. Okay? That's something we know. Sine 0 is 0. If you look at the sine graph, so this is sine graph. So sine 0 is 0. So that means this is a infinite times 0 problem. Okay, infinite times 0 is like indeterminate situation. But we can use some tricks here. You can use a L'Hopital's rule if you want, but it would be easier if you can use some other facts. This can be complicated because we have 1 over n. So without a derivative, it can be complicated. So we're gonna make some nice arrangement here. So how we gonna do this here is, let's say, so what we need is limit n goes to infinity. I'm gonna put star here because it's like a really nice argument. An and the limit n goes to infinity. We have n sine 1 over n. What we're going to do is we're going to divide the top and bottom by n to create, the whole argument is to create this exact same number there, 1 over n. That's the whole point. We're going to create 1 over n. So how to do that? We're going to divide the top and bottom by n. If you do that, then you're going to get sine 1 over n here, and then if you divide the numerator by n get cancelled, by the bottom you get 1 over n. Now we can make a really nice argument. So what will happen when n goes to infinity? When n goes to infinity, so we notice few things. One thing we notice is these are the same, so this has to be the same. Okay, if it is not the same, you have to make it the same. Okay, so that's one thing, it has to be the same. So those two are the same. Okay, same. And also 1 over n goes to 0. So, and then we know a result. Remember one result from calculus which says that, so we can use this result here. It says that the limit when x goes to 0, sine x over x equals 1. So that means if x goes to 0, if these two numbers are the same, these numbers are the same, this has to go to 0. So that means in this case, that's exactly what happened. Is 1 over n, 1 over n, which are the same. So that means this limit is simply 1. That's very interesting. So it is 1. Okay, so it goes to 1. So that means you can see an goes to 1 as n goes to infinity. That means the sequence converge. Okay, so converges. converges to 1. So this is a really nice argument. So remember, like, how we can make some arrangements there. So we use one of the calculus result here. So we use this one from calculus. And also we can make it upside down. X over sine x also goes to 1. Okay, so you can write x over 1. So you can also write limit x goes to 0, x over sine x. That also goes to 1. Good. So let's look at another variation. So how about if we slightly change the problem? So let's say we have a n, which is n sine 1 over n squared. So we can make a similar argument here, because you can see this is infinity, and again 1 over n squared goes to 0. So this goes to 0, so sine 0 is 0. So infinity times 0 problem. Okay, so we try to make it a 0 over 0 or infinity over infinity problem. But remember, here we didn't use a L'Hopital's rule, but we use like a nice argument from calculus. Good. So the point is, we try to create 1 over n squared. So how to do that? So one thing we can do is we can divide. So we have a n. So what we can do is okay. So I'm going to write the problem here. So what we try to do is we try to find the limit when n goes to infinity. That's the only test we do. Okay. So it's the limit n goes to infinity. So we have n sine 1 over n squared, which is inside. So what we're trying to do is we try to create the exact same term here. So to do that, what we can do is we can divide the numerator and the denominator by 1 over n squared. So that means if you do that, what do you get? So if you divide the numerator and denominator by 1 over n squared, here if you divide by 1 over n squared, you get, so I'm going to rewrite this. So you get, if you divide the numerator by 1 over, if you divide the numerator by n squared, you get 1 over n. That's what you get from the numerator. From the denominator, you get 1 over n squared. Okay, so that's clear. From the numerator, you get 1 over n. You simply divide the top and bottom by n squared. Divide the top and bottom by n squared. If you do that, in the top you get 1 over n, in the bottom you get 1 n squared. Now you can see these two are the same. So that means we can do the same argument. That means this limit is simply 1. So this is simply 1. So that means this is 1, but 1 over n goes to 0. That means 1 times 0. So which is 0. Okay, so it's 0. So this limit is 0. The earlier one is 1. So that means so an converges to 0. Good. So that's about that. So let's continue. So you can see like there's are really nice problems, and then you can try these problems. So these are, I'm going to give you some practice problem for you to try. So you can try these. So how about these sequences? So let's say n sine maybe pi over n. So it's not just 1 but something else. And then you can also try n squared sine 1 over n. And then let's make it a little complicated. Negative 1 to the nth power n cube sine 1 over n cube. I'm going to give you the answer for this one. This actually does not exist. See, why is that? Okay, so you should get does not exist for that. And then how about we put cosine? So n cosine 1 over n. So think of the cosine graph at 0. And then how about a sequence where the nth term is given by tan? So n tan 1 over n. Okay, so you can try those problems as practice problems, but the argument would be very similar to what we do here. Okay, and then the next one is this, the last one. what we call the continuous function theorem. So we can try that. So this is another major result of that. So the last one, what we call the continuous function theorem. Continuous functions, continuous functions theorem. Continuous functions theorem. Good. So what it says that, so it's a very powerful result. It says that if it has a continuous function, you can simply bring the limit inside. So so let's try the theorem. So let's say if the limit of a sequence an equal L, so you get some number L. Doesn't look like L, it's look like E L, and here's a function, and the f is continuous at this value L. Okay, there's a function which is continuous at L. If that is the case, then this is true. Then it says that the limit of the sequence generated by fan, because this is a, so you can see if you plug in an value to a function f, it's going to create a bunch of numbers. That means it's going to create a sequence. So if you try to find the limit of this sequence, this is exactly what we can do, is we can bring the limit inside. That's what it says. You can bring the limit inside an. So just bring the limit inside, and then, but this is, we know that L, so this one is simply equal to L. So that means what you get is FL. So that's the result. So what we remember is you can bring the limit inside. So that's what you remember. Okay? That's what we call the continuous function theorem. When the function f is continuous, you can bring the limit inside. So this is a very powerful result. Okay, so I'm going to say very important. So very important. Okay, let's do like maybe two problems from that. Um, so how about this one? Let's say you have a sequence an which is sine 3 pi n cube minus 1 divided by 6 n cube plus n plus maybe 10 to the cube, like a large number. Since n goes to infinity, it doesn't really matter what you have here. It can be million or billion, it doesn't matter because n goes to infinity. So we disregard that number. Now we know that this is a sine function. So we can say since the y equals sine x is continuous, we know that it's a continuous everywhere, continuous. Then what we can do is limit n goes to infinity an is simply, you can say, I'm going to write everything, so it's going to take some time. So sine, we can write everything 3 pi n cube minus 1 over 6 n cube plus n plus 10 to the 3. So what you can do is we can bring the limit inside because sine is continuous function. So we're going to bring the limit inside of the function. So that's the result. So it's 3 pi n cube minus 1, 6 n cube plus n plus 10 cube. Okay, now it's just a basic limit problem. You only consider the dominating term, you can consider this and that because those are only the dominating terms. So let's consider that. So that means sine, we can take the limit of that. So it's a limit n goes to infinity 3 pi n cube over 6 n cube is exactly the same, and you can see this and that get cancels, and also 3 and 6 get cancelled, you get pi over 2. So that means you simply get sine pi over 2. But we know that if you look at the sine graph, so what's the sine graph? Sine graph goes like that. So sine graph goes like that. So this is 0, and then we have pi. So that means at pi over 2, which is 1. Pi over 2, which is 1. So that means you get 1. So which is a finite number. So that means the sequence converges. Okay, the sequence converges to 1. Good. So let's do one more problem from that, because this is like a very nice result. Let's do something that have tan inverse. The tan inverse also a continuous function. So an, which is tan inverse. How about this one? Tan inverse. Let's say this one. We can use one of the results that we used earlier. So n sine 1 over n, like that. So we know how to do now. We tried this one before. So that means this is going to be really quick. Because tan inverse is a nice continuous function. What's the graph of tan inverse x? You know that the tan inverse x is in between two values, negative pi by 2 and positive pi by 2. So tan inverse goes like that and goes like that. So it is pi over 2, negative pi over 2, like that. So that's a tan inverse graph. So now, this is a nice continuous function. It's everywhere. So limit n goes to infinity, an, which is the limit n goes to infinity, tan inverse n sine 1 over n is continuous function. Bring the limit inside. So n sine 1 over n, and we notice that this is an infinity and a 0 type problem. So that means we try to make it infinity or 0 or 0. So we therefore that we divide by n top and bottom to create the exact same term in the numerator and the denominator. So that means this is tan inverse limit n goes to infinity. If you divide by n, the top and bottom, n get cancelled here. In the bottom, you get 1 over n. Now you notice that they are the same, but they goes to 0. Both goes to 0. So it's a 0 over 0. That means it is 1. So that means this is simply tan inverse 1, because the limit is 1. Okay, we just saw that this limit is 1. So tan inverse 1 is pi over 4. The reason is tan, since tan pi over 4 is equal to 1. Okay, since it's equal to 1, tan inverse 1 equal pi over 4. Very good. So that means the sequence in converges to pi over 4. Good. Yeah, so let's just write some other facts, not big results here. So some other, I'm going to say, important limits. So there are a few other limits that are important. So there are actually 4. So one is the limit when n goes to infinity is nth root of n. If you have nth root of n, this also exactly equals to n 1 over n. That's nth root of n, and actually this is equal to 1. So when n goes to infinity, nth root of n equal 1. Okay, that's one of the fact. And another one is limit when n goes to infinity, nth root of any positive number. Nth root of any positive number is also 1. Here a has to be a positive number. Okay, otherwise you have to have the absolute value. It doesn't work for 0. So it's also 1. So that's the interesting part. Both 1 and 1. And then there's another one which says that the limit when n goes to infinity, xn over factorial n. So those are special sequences. Okay, so we can look at the nth term, and which is 0, for any x. This is very useful, very useful. This is also used in a series. And then also the last one is the limit n goes to infinity, 1 plus x over n to the nth power. So see the format. It is 1 plus x over n to the nth power for any x. This is simply e to the x. So this is one of the a result that we use everywhere in calculus. Okay, so again, this is for any x, for any x, can be positive, negative, 0, whatever. So yeah, so those are some of the important limits. So let's look at some problems how we can use these facts. So check whether converge or diverge these sequences. Okay, so so one is, let's say the nth term is given by yeah, so let's look at this sequence. Okay, so the sequence is this. Where the nth term is n minus 3 over n to the n. So if you have a sequence where the nth term is like that, so what's going to happen? So if you call this is the nth term, so what we do as before, take the limit, n goes to infinity, an, so it's the limit, n goes to infinity, n minus 3 over n to the n. What we need to do is we need to bring this to this type, this form. How to do that? You can simply divide by n. So that if you do that, then you get limit n goes to infinity. If you divide by n, it will be 1 minus 3 over n. That's what you get to the no, not 3. 3 is n. So n. And now you can see if you use the result here, x equal negative 3. So you can see in this problem x equal negative 3. So that's x with the negative sign. So that means this simply equal to e to the negative 3. Okay, or it is 1 over e3. Okay, and this is a final number. So that means the sequence has to converge to that value. So you can say the an sequence converges to e to the negative 3. Very good. Maybe another one. So you can see there are like interesting problems. So this can be useful for the for this exam and the final exam. So these like pretty much all the types that we have. And then let's say negative 3 to the n or factorial n, like that. And then this is like straightforward. N goes to infinity, an, which is equals to limit n goes to infinity, negative 3n or factorial. According to the previous result, it says that for any value here, this can converge to 0. So this is 0. Okay, because this has the format xn to n factorial. Here x equal negative 3, so it doesn't really matter what value. So that means the sequence converge. Perfect. And then let's have some other results that are useful in sequences. So I'm going to say other results. So one other result is, it says that the sequence converge absolutely, sequence, not the series. The sequence converge, absolute sequence converge, actually not just converge, it goes to 0. It goes to 0. If the absolute sequence goes to 0, then the original sequence also goes to 0. It has to be, because if you consider the absolute value goes to 0, that means, so the situation is like this. It can fluctuate. Okay, it can fluctuate like that, but it goes to 0. That's the kind of situation here. Okay, that's one result. And then the other one is what we normally call the sandwich theorem. Theorem. So what's a sandwich theorem? Some people call it squeeze theorem. It's the same thing. Sandwich theorem is like a sandwich. So it is an less than or equal bn less than or equal Cn for n greater than or equal n for after some n, not for all. That's the case, and the two uh, neighboring one, like a bounded one, goes to the same limit. So that means those two converge, those two sequences converge to the same one. So that means the limit n goes to infinity a n and the limit n goes to infinity c n. Those are the outside one, has the exact same value. That's very important. Have the exact same value. Then it says that then the sequence has to go to the same value. Then so n goes to infinity b and also should have the same value. I mean, that's obvious. Okay, the two outside one goes to that, so it's going to carry over. So it's like a graphical situation is this. So we have Cn sequence, which is a large one, and the An sequence like that, and the Bn. So Bn is like can be going like that. So that's the situation. It can go like that. So this is Cn, An, Bn. So you see, they all three goes to the same place. Okay, it has to be because it's kind of bounded. Okay, that's the idea. So it's going to converge to the same value L. Good. So let's try to and then also one last thing is what we call the monotone sequence theorem. Monotone sequence theorem. What's the monotone sequence theorem says that any bounded, what's a monotone? Monotone means one tone. That means it's a mono means one. So it means either increasing or decreasing. Increasing or decreasing. That's what we call monotone. One type, one tone. So any bounded monotone sequence converge. Any bounded monotone sequence converges. Okay, let's just do one example from that just to see how we can use it. So it says any bounded monotone sequence converge. Just do one example. So how about this one? Does the sequence given by an equal factorial n over n to the nth power. So like complicated problem. Converge or diverge? And you can see that factorial n and n to the n both grow indefinitely. So ask me whether it's converge or diverge. But you can see that n to the n grow much faster than factorial n. So this is the kind of argument we're going to do here. So you can see that you can write, so note that you can write an, which is factorial n over n to the n. Factorial means what? Which is 1 times 2 times 3 times like that to the n. In the bottom you have n many times. So for each one on the top, there's a one in the bottom. So you can kind of nicely factor this. So what I'm going to do, I'm going to write the first terms from the numerator and the denominator and write the rest exactly like before. So you're going to write this pair, that pair like that. So it's a 2 over n, 3 over n like that, and n over n. You can see every term except the last one, smaller than because we are talking about large n. Okay, so if you look at an n which is larger than 2, you can see that because you took a large n, so you can see each one is bigger than then 1 on the numerator. So that means this whole expression is you simply multiplying some numbers which are smaller than 1. So that means this whole expression is less than 1. Since this whole expression is less than 1, this has to be less than this number, right? So that means you can write this one, this whole thing is less than or equal to 1 over n. So that's true. And also we notice that this side, these numbers are all positive, you can put it 0 there. Okay, now what we have is we have 0 less than or equal an less than or equal 1 over n. Now what we do, take the limit. If you take the limit, so limit n goes to infinity 0 less than or equal limit n goes to infinity an, that we don't know. Here limit n goes to infinity 1 over n. Now you can see this is 0, this is also 0. That means by the sandwich theorem, this also has to be 0. Okay, because the two sides goes 0. So you can say by the sandwich theorem, the limit n goes to infinity an equals 0. So that means the sequence converge, an converges. Okay, so those are the kind of problems that you can do using the sequences argument. So so this will be useful for the final and the coming exams. Okay, thank you.